Hello everyone, welcome to the new part of titration curve in acid-base titration. In the previous chapters, we have learned the calculation of equilibrium concentration of hydrogen in different acid and base solutions. Then, in the acid-base titration process, how does the solution pH change with the successive addition of titrant? This is the topic we are going to learn today, acid-base titration curve. We'll discuss it with the examples of strong base titrating strong acid and strong base titrating weak acid. First, we talk about the case of strong base titrating strong acid. For example, use 0.1000 mol per liter sodium hydroxide to titrate 20.00 milliliter 0.1000 mol per liter hydrochloric acid. As sodium hydroxide in burette is added dropwise, the pH of solution in a Lamire flask changes accordingly. Several representative points are chosen to calculate the pH of system. The first point is before titration, when the addition of sodium hydroxide is 0. The hydrogen in solution mainly comes from the dissociation of hydrochloric acid. The concentration of hydrochloric acid is higher than 10 to the minus 6 power mol per liter. So the hydrogen concentration can be calculated based on the simplest formula of hydrogen concentration equals C equals 0.1000 mol per liter, and pH is known as 1. The second point is the stoichiometric point, when the added sodium hydroxide is 20 ml and reacts completely with hydrochloric acid, leaving the solution appearing as neutral. Hydrogen in system derives from water itself, that is, 1 times 10 to the minus 7th power mol per liter, and pH is 7. In the practical titration process, it's hard to make sure the titration endpoint and the stoichiometric point are coincident. However, as long as the endpoint falls in the 0.1% range before and after the stoichiometric point, the relative error can be controlled within 0.1%, meeting the requirements of accurate quantitative analysis. At the point pre-0.1% of the stoichiometric point, where 19.98 ml sodium hydroxide is added, the hydrogen of solution primarily depends on the excessive 0.02 ml hydrochloric acid. At this point, the concentration of hydrochloric acid is 5 times 10 to the minus 5th power mol per liter, still larger than 10 to the minus 6th power mol per liter. So the hydrogen of solution can be obtained based on the simplest formula, that is, hydrogen equals C, and the pH results in 4.3. At the point post 0.1% of the stoichiometric point, where 20.02 ml sodium hydroxide is added, the hydrogen concentration of solution primarily depends on the excessive 0.02 ml sodium hydroxide. The calculated concentration of sodium hydroxide is 5.0 times 10 to the minus 5th power mol per liter. And based on the simplest formula, it is obtained that hydroxide concentration equals 5.0 times 10 to the minus 5th power mol per liter. So pH equals 14 minus pOH equals 9.7. These are the pH calculation processes of 4 representative points. pH of other titration points can be calculated following the same strategy. This table can be obtained by summarizing this data. T% here is the titration percentage. We deduce the calculation formulas for hydrogen and hydroxide in solution before and after the stoichiometric point. Armed with these two formulas, it is very convenient to calculate solution pH at any point during the titration. The pH change between post and pre-0.1% of the stoichiometric point is called titration jump. Based on these data points, the titration curve can be obtained with titration percentage as x-axis and pH as y-axis. This curve can be divided into 3 regions, which are acid buffer area with low pH, base buffer area with high pH, and a titration jump area. In the titration jump area, that is, between post and pre 0.1% of the stoichiometric point, pH changes dramatically with very little addition of sodium hydroxide, which is called titration jump. Let's have a look at a little quiz. During the acid-base titration, which area of titration curve should the titration endpoint fall to make sure the relative error controlled within 0.1%? A. Base buffer area. B. Acid buffer area. C. Titration jump. D. Adding area. Terminating the titration case of strong base with strong acid. How is the pH change in the system of strong base with weak acid? How is the corresponding titration curve? Similarly, the titration of 0.1000 mol per liter sodium hydroxide with 20.00 ml 0.1000 mol per liter acetic acid will be taken as an example to illustrate these questions. Before the addition of sodium hydroxide, the system is weak acid. The hydrogen concentration in solution comes from the dissociation of water and acetic acid. With the successive addition of sodium hydroxide, acetic acid will react with sodium hydroxide to produce sodium acetate. Acetic acid and acetate are conjugate acid-base pairs and compose the buffer system. We still choose 4 representative points to analyze the pH of this system. The first position is still the initial point, where the solution is weak acid. It's actually the problem of calculating hydrogen of weak monoprotic acid. Since the conditions of CKa larger than 20 kW and C divided by Ka larger than 400 are qualified, hydrogen can be obtained based on the simplest formula, and pH is 2.85. At the pH position pre 0.1% of the stoichiometric point, the solution is a buffer system consisted of acetic acid and acetate with certain buffer capacity. The solution pH is calculated following the method of buffer solution. When 19.98 ml sodium hydroxide is added, concentration of conjugate acid, acetic acid, Ca, and the concentration of conjugate base, acetate, Cb, are calculated and substituted into the simplest formula to get the pH of 7.74. So the concentration of hydrogen and hydroxide can be easily obtained. Let's go back to the rigorous equation. The premise that it can be transformed to the simplest formula of buffer solution is C1 and C2 are way larger than concentration of hydrogen and hydroxide. According to our calculation results, the concentrations of acetic acid and acetate are indeed much higher than concentrations of hydrogen and hydroxide, so it is reasonable to apply the simplest formula. The third point is a stoichiometric point, where acetic acid reacts with sodium hydroxide completely. The alkalinity of the solution depends mainly on the dissociation of acetate. Since the conditions of CKb larger than 20 kW and C divided by Kb larger than 400 are qualified, hydroxide can be obtained based on the simplest formula. With the concentration of conjugated base acetate, pH is resulted as 8.72. At the pH position post 0.1% of the stoichiometric point, sodium hydroxide is added excessively and alkalinity of the solution depends mainly on the amount of sodium hydroxide. The relative data is the same as that of strong base reacting with strong acid. When excessive 0.02 ml sodium hydroxide is added, the calculated pH is 9.7. As for other titration points, the pH can be calculated following the same strategy. This is a table of summarized data at different titration points. Similar to the titration of strong base to strong acid, pH of other titration points can be obtained based on the calculation formulas of hydrogen and hydroxide before and after the stoichiometric point. Plot with these data. It can be seen from this image that the curve of strong base titrating weak acid resembles the curve of strong base titrating weak acid, but the titration jump is much smaller. We will continue to discuss these phenomena in further study. That's all for today. Thank you.